So my talk is about fluid coupling across models and dimensions. And when I signed up for the session, I called it from OpenFOAM to FEniCS. But I need to step down from that, and I just want to call it from OpenFOAM to Python, because in the end I wrote the complete Python interface on my own, and I wanted to wait until the FEniCS adapter I was able to integrate this. Afterwards, I want to couple this with FEniCS instead. So what I want to do, I think I'm the only session here talking about fluid coupling, right? And I think it is kind of a different sense to what we do in other applications, because in fluid coupling, we want to couple essentially the same thing, right? This is a flow solver, this is the same flow solver, and I want to couple these, right? It's not that I have a different quantity I want to compute on my other side. Ideally, these two things would coincide, right? So this is the idea for me for fluid coupling. But I want to do it differently, because on one side I have the fluid solver, and on the other side I want to have a reduced one in whatever sense we want, right? It should be cheaper. It should in most cases be dimensionally reduced. So we have 3D here, we have 1D here. Maybe we have even a different flow model here, and they kind of need to talk to each other. And by starting that, I first want to come up with an application where it actually matters, right? So this is an application that was developed. So the idea is, oh, sorry. The idea is hydropower storage systems, and they work essentially, the idea is very simple. We have 2 ponds of water. One is on top, one is at the bottom, and you have a turbine in between. And if the water flows from top to bottom, you pull it through a turbine, generate electricity. If you have spare electricity, you can pump the water up again. And these are things that are actually, people want to build these things, and now they go to the hydraulics people and be like, design me a thing, right? How do we design it? And that's an open question. And there was some PhD work in Aachen based on that, one from Professor Elena Pummer. She's now a professor in Norway, where they're also interested in these things. And currently, how this design process works is handmade, right? People are doing essentially OpenFOAM simulations in 3D, and then they do one iteration on one design, then they sit together, and there's no automatic way of doing design optimization there. And we thought about, can we do something about it? But if we want to do something automatic, for sure we need to be more efficient, right? And this is where this little project came along, and this is how the vision goes, right? On the top right, you see how such a design that I try to run fully in OpenFOAM works, even if this kind of model has like a 500K number of cells, we need to run it. And where we want to be like is, essentially the idea for me is go down in your dimensionality where it's possible, right? And if you look at this design here, we have on the top right, there's an inflow area, right, where the water comes on. And there, certainly we need 3D, right? I don't see a way how we can easily get away with something that is not 3D, right? And if we talk about reduced order models, they have assumptions. For example, they are hydrostatic. There's a free surface. But in this area, maybe the thing is fully flooded, right? There's no free surface anywhere. So can we even go to reduced order models? People try to do the full thing in a 2D, in a 1D model, and they have difficulties. And my claim is yes, because if you violate assumptions, you will introduce errors and they will propagate, right? So let's do it properly, and properly for me means you design it like on the top bottom left. Do the 3D part where 3D is needed, and then after a point where you can clearly define, yeah, here's a good way to bridge, then let's bridge over to 2D or even 1D. And here you see these channels where the water will eventually flow down. They're also quite easy in design, right? So this is good because it makes a good test case for me. Now the question is, what do we choose, right? What do we choose as a reduced order model? And the very classic problem that people have done here is to couple OpenFOAM with what is called the shallow water equations. That if you think of a 3D model for hydraulics, like the K epsilon interform two-phase flow solver, right? That's the standard thing that people use. And shallow water equations is like, reduce it as much as you can, right? Then you end up with shallow water. It is essentially hydrostatic, so the pressure is as easy as it can be in terms of solving it. You can have explicit schemes. You don't need to solve the Poisson equation, whatever. So it's very cheap and easy, and it's trivial to do it on a GPU even, right? So if I would call the inflow part, the 3D part is expensive, the other one is instantaneous, right? If you compare the two in terms of simulation times. So I would say, why shallow water, right? Can't we do a little more there? I mean, because even if the left part, the reduced order part, is 50, 100 times more expensive, but still in the setting of a reduced order model, it is a way better candidate to couple because it has more information, and then the exchange interface between this four information is maybe more aligned with each other. So this is kind of my vision. And of course, I'm biased because my PhD work is about these reduced order models, right? It's not about coupling. This is only an afterthought, right? I'm coming from this bottom left corner here where people are in this field of using reduced order models. And if you're in this field, there's a zoo of models, right? If you have a water wave coming up the shore, shallow water isn't doing the trick anymore because the wave is breaking, right? If you have a tsunami propagating from its origin to the shore, you need a different model again. You then want to couple to another model. Then you want to go into your city and have the fluid structure interaction, you again have another model, right? And all of them have their purposes. So I think this is an ideal way to introduce a framework where we can easily transition between all of these. So this is my vision. And how do I want to do this? So as PhD projects go, in my PhD project, I'm also developing code, which is on the side of these reduced order models. And the mission is there essentially put them all in one, right? And how do you put many different reduced order free surface flow models in one? It's to find a language where they all align in, and it's about their state variables, right? And state variables are the things that you compute. For OpenFOAM two-phase flow solver, we have a value alpha that you see here that encodes is there water or is there air? And then we have classical things, right? The velocity of our fluid and the pressure. So these are the things that also, as I would say, many people understand, right? This is intuitive. And now let's look at some of the models that exist on the other side, right? And there it's getting really fuzzy because every mathematician, when they reduce the stuff, they start here, they integrate, they build in assumptions, and they come up with a model. And for each variable, they kind of have a new name, right? So for example, in this model here, we have 2 U's, we have 3 P's. Then if you have more dimension, they even get more, right? What does these represent? And I would say this is hard, right? If you don't read the paper carefully, you're out of depth immediately. So I would say that each of these models, but what they comply on, they hate state variables. And I would say they need to talk to each other, and that's what I'm responsible for. And how do I let them talk to each other? I essentially say, if you're a reduced order model, then you better know how you were derived in the first place. So you better know how to project back to the thing, because this is the language that we can talk to each other. So this is now what I'm trying to do. But now, trying to do this in a coupling way, now where the complications are coming in, right? This slide is certainly only there to intimidate you. That's why there are so many variables. But let's look at the big picture, right? On the left-hand side, we have like a 3D block. It needs to talk to my 2D reduced domain. And it does so by the blue part, right? We need to, each of these stripes, they need to reduce their data into a single point by however your model was derived. Okay, but now if we think about coupling, we want to have different cases, right? So if the flow direction, and by flow direction, I don't necessarily mean velocity, is going from left to right, right? Then there's a certain set of boundary conditions that a mathematician would call well posed. So this is a problem that I probably want to solve. But now in this case, for shallow water, this depends now on the cases, right? It can be subcritical or supercritical. For aerodynamics, the thing would be subsonic or supersonic. So these are cases that kind of say which variables do you want to choose, right? And for this particular one, if you want to couple OpenFOAM with shallow water, this was done in the dissertation of Mintgen in 2018. He did this completely in OpenFOAM. Then we already have 4 cases that we need to differentiate at each coupling step. Essentially, in which of these phases are we? Based on that, we exchange information, build our boundary conditions, and we can move on. So, and to only iterate about 2 of these, what do they mean? Typically, they are either Dirichlet or Neumann type boundary conditions, unless we want to do something fancy. But in his dissertation, this is what he tried out, and it works well. So in this state of my project, starting with coupling, I'm like, let's just reproduce what he has already done and try to find a way to build this in OpenFOAM. And this boundary condition is essentially a 0 Neumann boundary condition for the water height on my shallow water flow solver. And a second one says, and that's why I introduced this notation of f of q, here we want to impose a Dirichlet condition on my discharge, so the water height multiplied by fluid velocity, built on the information from the other side, right? So this is where information comes in from OpenFOAM, and I need to convert this. I need to go down this triangle here, reduce my data to this single point. All right, once I started by doing that with preCICE, I essentially first looked what is already there. So when I found two nice things that I based my existing work on, one is the partition two-phase flow example that was there. Why I like this particular example, it is using the right OpenFOAM solver for me, right? So this is a two-phase flow, we have air, we have water. Essentially, it's a one-way coupling going from here to here. This is what it does. But I need to have bidirectional coupling, right? I don't know from which side am I coming, in which boundary condition am I in. So I checked out this partition backwards facing step example where they don't use a two-phase flow solver. This is a single phase, but they nicely show here that interface position, that here the water or the flow direction is in this direction, and here we have this circulation, right? So this seems to be the right setup for me, and this is the right solver. So this is where I started from. Now investigating, do I have everything that I need from the OpenFOAM adapter? And this is my current conclusion, and I would say not quite, but nearly good enough. So the only thing where I see a problem is the supercritical case, because we cannot make the distinction of in which side we are on the flux variable alone, right? This does not differentiate the state. And this is what I think the OpenFOAM adapter currently does, if I understand it correctly. And therefore, let's look at a particular one. If we have a subcritical flow coming from the shallow water side, so really a shooting wave, then what I would like to describe is the alpha value itself, and I think this is currently not possible. Therefore, I dabbled in implementing my own coupled kind of variables in the OpenFOAM adapter, which I called then coupled alpha or coupled Dirichlet-Neumann condition, something along these lines, in order to realize these things. And of the story is it's not quite working yet, so I left the rest out of my talk, but if you're doing something similar, I'm happy to talk to you about it. Continuing with my work, now the question is, preCICE offers me a lot of utility to do mapping, right? Do I want to use preCICE to go from 3D to 2D, or do I not want to do it, right? And I deliberately decided on not doing it. And why is that? So what do I do? When I couple, here's preCICE setting, here's OpenFOAM. Oh, sorry, that was the bad button. Here's my OpenFOAM sitting with a 3D mesh, and what I want to couple is to my side of my solver, and I use the exact same surface mesh. Why do I do that? Because it's upfront not clear how this reduction works. But who knows about this reduction? It's my reduced order model, right? I enforce on my side that my model knows how it went from 3D Navier-Stokes to its reduced part. So I also better know how this projection works, and then I don't need to build for n different models an own adapter into preCICE. So this is how it currently works, and it makes things very easy for me because essentially it doesn't matter, right? These points are always working, so a nearest neighbor mapping is always exact, right? So this is what I get from there. And this is how I try to move on. So this is then my coupling config, and it looks as messy as it gets when you have bidirectional coupling. So essentially all flow variables need to be written to the other side and sent back, right? And this is how such a config works. So each entry needs to be doubled essentially. For example, the velocity goes from one side to the other, and then a similar variable called velocity back that goes from this side to this side, right? And this is how we do it with all my field variables. This is how I took the config essentially based on one of the examples. How's the time? All right. Then another thing, I use parallel implicit coupling here. The parallel is not so important for me right now, but I think the implicit currently is. Because what is the main problem here? Kind of both interfaces, they need to, based on this work, what is a hidden thing in here is that if my right-hand side, if my shallow water solver says, yeah, I'm subcritical, then the other side better also says it's subcritical, right? I mean, I don't even know mathematically what happens if one side says, I'm supercritical, the other side, no, I'm subcritical, right? This can happen in practice, but mathematically, do they need to match? Or do they only care about their own boundary conditions in order to be well posed, right? This is a mathematical problem. I don't know the correct answer, but I also read nothing about it whoever asked this question. So if you're a mathematician and know about these things, please help me out here. So I need implicit coupling so they kind of have some time to essentially balance and talk to each other and kind of decide on one thing, what they should do. And this is now some preliminary results on a simple subcritical dam break. On the left-hand side, we have OpenFOAM, on the right-hand side, we have shallow water. And the thing I would like you to observe here is, when you look at these white lines that are contour lines, is OpenFOAM, there is the fancy contour lines because the velocity flow is not uniform. And the moment it crosses over to shallow flow, it's an assumption, there the velocity gets uniform, right? So kind of have a break in information, which is what it should do because we are reduced. But the thing is this critical, right? And I think for coupling itself, does this increase our coupling iterations that we need? I think this is an open question, right? I don't know. If we could recover a better right-hand side, would we need less iterations? I would only like to pose this question. I don't have an answer for this yet. But there's another more severe problem, conservation of momentum. We can only, if we go to reduced order model like shallow water, only conserve mass. We cannot conserve momentum. And why is that? If we look at the momentum flux, this is the momentum flux of OpenFOAM. This is the momentum flux of shallow water, which is a block profile and the velocity. And you cannot ensure that they are the same, right? In fact, if your velocity profile is not a block profile, you have no way to conserve momentum, right? And then there are other things, for example, the pressure. Here we have the pressure on the shallow flow side, which is hydrostatic. If you're non-hydrostatic, of course, we violate these, right? But I would say this one we can easily design by choosing the right interface position. This one is a little harder. And then there's the viscous stresses. This is typically the modeling task of your reduced order model. So what I'm working on is this side here. I would like to have a better model here to bridge this. And how do I do this? I think I have 5 minutes left, right? And this is now where my PhD comes in, right? I would like to have a better transition in the conservation of momentum by having a better conservative or conservation of the flux. And how do we do this, right? This is what shallow water does. If the red line represents your classical velocity profile in your flow, then what shallow water does, it takes the mean of that, and this is my profile, right? This is my block profile, move on. But what if we use a similar derivation, but instead of using a block profile, we assume something else? Let's assume a linear velocity profile, right? Then we can recover more. And this is how we can do this. We choose a basis function that is constant plus a linear part, and then we get two coefficients instead of my block profile velocity. We get a momentum equation for my block profile and a momentum equation for my linear contribution, whatever you want to phrase it. And using such a generic formula, which is nothing else than representing a function in terms of a basis representation, right, a polynomial representation, but then doing the math for the derivation, we can generate n different models, right? And this is what I'm working on. We call this a hierarchy of models because we don't want to fix it in the beginning. We want to say you can adapt it, or we can even do it adaptively and choose the right number of my model size in order to fit the data. And this is what I was doing anyway, and then I was thinking about this flux coupling and how we can conserve momentum. And this is what we can immediately observe, right? If we now try to observe, and this is what, when I did a one directional coupling from the OpenFOAM side to a shallow water type side in our solver Zoomy, then you see here a lot of velocity profiles, what we call them, right? At different positions, but in black in the background, you can see the sign of the OpenFOAM solution. And then the blue line is always what shallow water does. And of course, it does not comply to the data because it can't. But and then if you increase the polynomial degree, and you fit better and better. And of course you do, right? Because this is what a linear or what a polynomial basis does, right? But then let's look at the errors at the interface, right? We can compute the errors here, and from shallow water, we have kind of the order of -2 in this example. by using a shallow moment model, that's what I'm doing, of level 8, so you have a polynomial up to polynomial basis 8, you can get up to 10 to the minus 5, right? So you can reduce this interface error. The question is, does this help you, right? And I would say, now this is up to modeling, right? But not up to coupling. Now we solved the coupling interface issue. Now you only need to come up with a good reduced order model, and then you solved your thing, right? So this is what my claim would be. And if we look here at the error improvement, it's like 30 times better at the interface, right? Of course, you need to use this information downstream, combine it with a good model. Now, how does this improve it? Looking back at this same little 1D test case that I had before, this was the result that we had. This is how the OpenFOAM solution looks like if you do monolithic OpenFOAM. And this is what you get kind of now with a shallow moment 4 model. So polynomial degree of order 4. And you can kind of that interface here, the isolines are more or less smooth over, right? So the interface gets a good reconstruction. If we look further back into the flow, then we are off. Why is that? Because you need to find the right model here that does the right thing with your momentum that you get. Do you have the right viscous stresses, right? Can you build them in? And here we essentially took an inviscid model, so there's no chance that we recover the OpenFOAM solution here, because what we need to do in order to do that, my proposition is we need to have an OpenFOAM model, let's say K epsilon 3D here, and then we need to have a reduced order K epsilon model on the other side, right? This would be, for me, a consistent coupling with which we can achieve, hopefully, the this view on the other side. All right, takeaways. From my side, of course, I think there's more than one reduced order model for fluid flow. There's more than just shallow water, and we should think about these things if we want to couple. There's a lot about the boundary conditions and a lot of issues with these. I only showed you this big table of equations. This was only for the shallow water case, and it gets worse and worse, right? If you have one more equation, you have 9 cases, right? It increases with the power. So the question is coupling via boundary conditions even the right approach? Because we need to be looking at the invariances of the problem, right? And if the problem size increases, it gets more and more complicated. So the question is, maybe should we rather do something else and have like overlapping volume regions and try to couple this instead in order to avoid the boundaries altogether? This is one of the things that I'm looking forward to explore in the future after we figured out this boundary surface coupling first.
Thank you very much, Ingo. Questions?
Very nice talk, but I think, so just to get me right, when you're coupling from the shallow water to the full model, you're just reinterpreting the depth average U as a constant U.
Yes, I mean, this is, let's say, the most simple one, right? This is not the one that people do. You can enrich this data, right?
Yeah, so immediately on the left of the boundary, you've got the full U profile, including its shape. Yeah. So you can reinterpret the U bar using the shape on the left of the boundary, and you get much more accurate coupling.
Yes.
Okay, but that's cheaper than doing moments.
Yes, so this is, I mean, I deliberately didn't do it here so that it's getting more pronounced where the issue, I think, is, right? But I would call this enrichment of your data that you have, right? But I think it is kind of a little, it's not really cheated, right? It's compliant,
yeah,
but it's kind of, you're not using this information downstream. You're only helping your coupling interface a little by enforcing whatever's on the left, right? But this is...
Well, you're enforcing the shape on the left, yes. not the total mass or momentum. But you are reinterpreting the shape from the left. And it will give you much more consistent data, I think. Yes,
but only for one type of boundary condition, right? Only for the type of boundary conditions where the profile actually should come from the left, right? In all the cases where you have a shooting flow from your shallow water type, I would say this is inconsistent, right? I would say, yes, this is what people do, but I would claim that in only some of the cases, this is truly the correct thing to do.
Well, okay, yeah, I'll talk to you later.
Yeah.
But yeah, very nice talk.
Next question. So at least for the linear case, when you couple two hyperbolic equations, there is analysis by Jan Nordström using the summation by parts framework. Okay. That should give you which boundary conditions give you well-posedness. Okay. That might be useful for you. And then a question, I didn't really understand why you have such a problem with momentum, because both equations have a momentum equation.
Yes.
So you should be able to enforce continuity of momentum.
But the momentum flux needs to be the same in order to conserve momentum across the boundary. But the momentum flux is the squared thing, right? And the integral of the squared thing. But if one is a block profile and the other one is not, right, then you can only conserve the mass flux. But the momentum flux...
Yeah, but isn't that an averaging process from one dimension to the other?
Yes, but in this averaging process, you do essentially the momentum conservation across your 3D domain, right? You only conserve the average.
Exactly. Yeah,
Yes,
yeah.
But, I mean,
But that you should be able to get.
Yes, you conserve the average, but you don't. Yes. Yes, I would agree on that. The question is this what we truly, is this enough?
I was just going to come to that. So I only know this stuff from the granular community. You show water models all the time. But when they do this, they introduce a shape factor, which is the difference between the average of the square momentum, the average of the square velocity, and the average velocity squared. And that is to helping. Then that extra degree of freedom allows you to conserve mass and momentum separately.
Yes.
So because it introduces you an extra parameter.
But the shape factor is built on, for example, the assumption of a log profile, right? Then you compute the shape factor, so it only holds for this one. I mean,
Yeah,
that's,
I agree.
that's where we are
I
coming
agree.
from,
This
right?
enforces mass and momentum conservation for a given profile. But again, on the full 3D model, you have the profile. So yes, it is true at the interface. What happens downstream is now up an approximation.
Yes.
But it is true at the interface.
I fully agree, right?
Okay.
This is where this also comes from, yes.
So just in fluids, they do use the shape factor because your
No,
formulation
we
didn't
don't
have
use
it.
it deliberately because we want to essentially dynamically construct it from the shallow water side, right? So essentially we want to get rid of the shape factor and instead of our models there that can tell you how does the actual profile look like that is coming from the reduced order side.
Okay, thank you.
More questions?
Do you know the direct mesh access feature in preCICE?
No.
No. Okay. That could be something we could try out on Friday. I think it would simplify your setup quite a bit.
Cool.
Not solve your problems, but make your software nicer.
More questions? All right. I have many for you, but I will keep them for actual discussion. All right, then thank you all very much. I have, yeah, thank you.